this is our FTTH architecture, from the OLT to the ODF to the cabinet to the first splitting, second splitting, then to the ONU. Then we're in this design, we want to go for underground deployment, and our physical distance from the location we're taking as case study here is from K2 to Magodo, and the distance measured for it is 6.5 kilometers. So we want to determine how many manhole will be along this 6.5 kilometers, and we also agree that 150 meter per manhole. For every 150 meter, there is always a manhole. So we take our 6.5 kilometers, divide it by 150 meters to get our number of manhole, which was 43 manholes. Now we have to calculate for slacks the excess we leave for troubleshooting. So for that slacks, in each slacks, we are going to have 7 meters of slacks. In the initial manhole, we are going to have 7 meters of slacks, and we have for 3 manholes. So we did for 3 times 7 meters, then we arrived at 0.301 kilometers. Then what we got, the total length of slacks that we got, we added it to the distance of K2 from K2 to Magodo. Then we have the total cable length to be 6.5 kilometers plus 0.301 kilometers, which gave us 6.801 kilometers. So that's our total cable length. Now we are going to losses. The connector loss. The first one is the connector loss, and you can see here we have 10 connectors, 10 connections. How do we arrive at that? From the OLT to the ODF, there is a patch cord which connects to the OLT and also to the ODF. So that is 2 connections. From the ODF to the cabinet, another patch cord, another 2 connections is taking place, making 4. Then from the cabinet, there's another connector, there's another coupler that another connector is taken out of the cabinet, making how many now? 5. Then once it goes into this case, the pigtail here is connecting. There is a pigtail inside this splitter box that is being connected to a coupler. That is another connection. That is making 6. Then there is another connection that is happening again that actually splits the optical power inside the splitter box. That is another connection. Now making 7. Then the same thing happens there. The 2 connections that I explained there happening there. That is 9. Then from the one taking it out from this place is coming to the ONU. So that is another connection, making a total of 10 connections. So that 10 connection is what we have here. And we know for every connection loss, for every connection there is always a 0.2 dB loss. So we did 10 times 0.2 dB, which we arrive at 2 dB. So that is the loss for the connector. For the splitter loss, since we are using 1:4 splitter and 1:8 splitter, we take each losses of those splitter, and for 1:4 splitter we have 6 dB, and for 1:8 splitter we have 10 dB, which we have here and we have here. So we are going to take the total of the splitter loss. So 6 dB plus 10 dB, we have at 16 dB. Then we go to the cable loss. For the cable loss, per kilometer of cable, we always have a 0.35 dB. And since we had our total cable length to be 6.801 kilometer, we multiplied by the 0.35 dB, then we arrive at 2.38 dB. So assuming Splice loss is negligible, is not significant enough to be considered, then we just calculate the total losses that we have. So we'll do the connector loss plus the splitter loss plus the cable loss, which we have here. 2 dB plus 16 dB plus 2.38 dB will give us your total loss, which is 20.38 dB. Now, we want to determine the receiving power. From the OLT, the optical power that is being transmitted out from the OLT, in this case, we are taking it to be +5. So, we represent that transmitter power with Tx is equals +5. So, the formula for receiving power is, the receiving power is represented by Rx and is equals to Tx minus TL, which means transmission power minus transmission power minus total loss, which our transmission power is 5 and our total loss is 20.3 dB. So you do the math and you get minus 15.38 dB, and which is also within the acceptable range of minus 8 dB to minus 26 dB. So at the end of the day, this guy ONT will be receiving minus 15.38 dB.
Thank you.